Okay, so today I want to talk to you about quadratic word problems. Okay, we've been dealing with quadratics this whole unit. So why do you even care about them? Turns out you actually care about them a whole lot because quadratics are everywhere. If you, let's say, kick a soccer ball, or if you drop something out of a plane, or if you jump off of a cliff, anything like that, the shape that the object travels in is a parabola. Okay, so let's go back to the kicking the soccer ball. If you're jumping off a cliff, hopefully it's into water, like in a safe scenario, right? And if you're dropping something out of a plane, hopefully it's like supplies for someone or something like that. Okay, so anyway, um, here's the ground. And let's imagine that you're going to take a soccer ball, it's on the ground, and you're going to kick it. It's going to follow a path, something like that. Okay, so a couple of things I might want to know. How high does that soccer ball ever get? How long does it take to get to that highest point? How long is it going to take for it to hit the ground? Okay, so usually what we do, wherever the object starts, we kind of go ahead and create, we kind of put that object right at the origin. So imagine that I have an X and a Y axis here, right? So here's my Y-axis, my X-axis. And I put the soccer ball, I'm going to start the whole thing off with the soccer ball at 0, 0. Okay. Sometimes if something doesn't start on the ground and it starts like, if you jump off a cliff into water, you're not starting at ground level or sea level, right? You're starting up above. So we'll look at that scenario in a minute. But a couple of things are going to happen. If it goes from the ground all the way back to the ground, you're going to be looking at this piece of the parabola that looks like this, right? I don't really care about, yes, the parabola would keep going this way and this way, but since this is a real life scenario, like the soccer ball's not ever going to go over here, so I don't really care about negative x values in this case. Same thing over here. Once the ball hits the ground right here, I mean, I don't care about it after that. So for the most part, most of our graphs are going to work like this. The x coordinates are going to be time, and then your y coordinate is going to be height. Okay, so the vast majority of the ones that we are going to look at look like this. So we'll be graphing the height of the object over time. All right, so if I want to know how high this ball ever gets, well, where is that going to happen on my graph? Don't you think it would happen right here? Oops. Right here. And what is that point when we're talking about a parabola? If you said that's the vertex, bingo bango, right? That's it. That's exactly where that information is going to be. So at the vertex, you're going to have two things, right? The vertex is always an ordered pair, x comma y. So let's write it like this. At vertex, you're going to have the x coordinate and the y coordinate. They're going to tell you different things. The x coordinate, remember, refers to time. So whatever the x coordinate of your vertex is tells you how long it took to get to that highest point. It doesn't tell you what the highest point is, just tells you how long it took to get there. So this is time it took to get to highest point. Okay, and then your y coordinate, that's going to represent how high it actually went, right? Because the y coordinate refers to height. So how high it went. Okay, so that's two very important bits of information that you find right at the vertex. And you guys already know how to find the vertex, hopefully. If you don't, maybe you go back. But negative b over 2a, if your equation is in standard form, which almost all of these are going to be. So we'll be doing negative b over 2a and then plugging that value back into the function to figure out what the y coordinate is. Okay, so once you have those two, you have the answer to both of those questions. Okay, of course, that's not all we ask you though. We also want to know things like, okay, well, when did the ball hit the ground over here? Right? So, well, take a look at the graph. What is that value? Well, isn't that value an x-intercept? You have, if it started at the ground, you already know one of the x-intercepts is going to be 0. But if you could find the other x-intercept, now that is going to tell you how long it took to get where, for the ball to go all the way up and come all the way back down. And it makes sense because when the ball hits the ground, won't the height be 0? So you're going to plug in 0 for y and then go ahead and solve for x. Okay, so to find this point, we are going to find x coordinate, which means plug in 0 for y and solve the quadratic. Plug in 0 for y and solve. Okay, you're going to get two values. One of those values should be 0 if this is your setup, and the other value is going to be your answer, right? However long it took. Okay, so I said there was another scenario. What happens if you aren't starting at the ground? What if you're starting some value up? So let's go ahead and erase all of this. Clear my drawing. Yes, okay, good. So, all right, new scenario. Let's say we have, let's do the cliff, right? So let's say that there's a cliff over here, and then there's water down here. So you are going to safely jump off the cliff. And so, I don't know, I'm not gonna really draw you very well. So I'm just gonna draw your path, okay? That's probably better. So you went, you left the cliff, and you're gonna land in the water, okay? So here's what we're gonna do. We are, let's see, I don't have too many colors left. We're gonna set it up kind of like this. So we're going to leave the water as sort of the 0 line. Okay, so in this scenario, you're not actually starting at the origin, you're starting at some value up here, which is going to be the height of the cliff. Okay, so, you know, we'll do an example problem in a minute, but think about the same things I'm going to ask you. I'm going to ask you, well, how high did you get? Doesn't that still occur at the vertex? Right? That's still going to happen at the vertex. That's still going to be the y coordinate of the vertex. How long it took you to get there, that's going to be the x coordinate of your vertex. So same as it was in the last scenario. Okay, how long is it going to take you to hit the water? That is still going to be the x-intercept, right? So you're still going to replace 0 with y. Sorry, other way around. Replace y with 0 and solve your quadratic. Now, the interesting thing when you do it in a scenario like this is that you're going to get two values, and one of them is going to be a negative, right? So if you're solving for x, you're trying to find this x-intercept right here, right? When you plug everything in and you solve, you plug in 0 for y, and you solve for x, you're going to get two x values. You're going to get some positive number here, but then you're going to get some negative x value. And remember, x is representing time. So you're going to be like, well, how can I have negative time? Well, think about, this is a parabola. Don't parabolas, they're symmetrical. It does keep going forever in both directions. So it does, the graph hits the x-axis somewhere in the negatives, but in real life that never happens. Okay, so that's why we're going to throw away that answer. It wouldn't make any sense. I can't have negative time. But mathematically, the graph has another x-intercept that's in the negatives. Okay, so I hope this makes sense so far. Oh, one other thing that I do want to point out, if you're looking at the example where you kick the soccer ball and it comes right back down, everything here is symmetrical. So if I knew that the highest point happened at, let's say 2 seconds, then, so if it took 2 seconds to do this, it's going to take 2 seconds to do this. So you do actually already know that that's going to be a 4, right? Because this is all symmetrical. In my newer scenario here, the bigger one that I have drawn out, it's not symmetrical right here, right? The time it took you to do this right here is nowhere near the time it took you to do this. So you can't get away with the same thing there. So even if I knew that this was 2 seconds, I have no idea what this is because that is not the same as this. Does that make sense? So you do, it's just a little helpful hint. If I am starting at the ground, returning to the ground, I can kind of get some of my answers a little bit easier if I remember the fact that the parabola is symmetrical, and I can kind of play that game. But you can't do that if you're not starting on the ground. Okay, so I have attached a worksheet for you to do. So I kind of want to, I was thinking maybe we could do like the first and the second ones together and kind of go from there. So if you have the sheet in front of you, that would be helpful. If you don't, I'm going to rewrite the function here. So let me just read it to you. It says Jason jumped off of a cliff. Oh, there you go. So Jason jumped off a cliff into the ocean, Acapulco, while vacationing with some friends. His height as a function of time could be modeled by the function, and I'll write it down for you in a minute, where t is the time in seconds and h is his height in feet. Okay, so here's the function. Okay, so in the very first question I asked you, how long did it take for Jason to reach his maximum height? Actually, before we even continue, if you are there, it does say on here that you can use a graphing calculator, and you absolutely can. I might try and show you how to do it on your phone or tablet or computer. You can use a really nice website that works as a graphing calculator very easily if you don't happen to have one at home. And if you are, just remember that you're going to replace the height with y, and you're going to use x's instead of t's. Okay, so any hoosers. Oh, there's not a, oh, there is an undo button on this. Okay, so here's our function. Part A is asking me, how long did it take for Jason to reach his maximum height? How long did it take? So I'm actually kind of going to sketch this again real quick. So again, we have the cliff. We're going to have some water. He's going to jump off the cliff and land in here. Okay, so I'm looking for the vertex. Is going to show me how high he ever got and how long it took me to get there. So which coordinate of the vertex do I need, the x or the y, for how long it took? Hopefully you're saying the x coordinate. Okay, the x coordinate is time, the y coordinate is height. All right, so when I find x comma y, I'm really finding time comma height, if you want to think of it that way. All right, so let's go ahead and find that vertex. Remember, I'm going to do negative b over 2a. So in this case, that'll be negative 16 over a negative 32. So it's going to be a positive 1/2. Okay, that is the x coordinate of my vertex, 1/2 comma, and now the something. So I would have to take 1/2 and plug it back into my equation to see what I get out for y. And just to save ourselves some time, you should get out 484 when you do that, if I'm taking 1/2 and plugging it back into the original function. Okay, so, and all of this makes sense, right? Think about it. You're jumping off of a cliff. So 1/2 a second to get to your highest point. Yeah, that's probably reasonable. If it was like 10 seconds, what do you have, a jetpack on? Like, that wouldn't make any sense. So 1/2 a second, yep. And you were already at, if you plug in 0 for t, so when you start, you were starting at 480 feet up. So to get to 484 feet, so you jumped up 4 feet. Yeah, I mean, I couldn't do it, but apparently Jason could jump up 4 feet. I'm assuming he has a running start. he's going to jump. So all of this seems reasonable. Okay, but anyway, my answer to part A comes from where? The x coordinate of the vertex. So it took him half of a second. Okay, and then part B, you already have the answer to. It's asking you what was the highest point that he reached. That's the y coordinate of the vertex. So that's going to be 484 feet. Okay, and then they are asking for a part C. How long after he jumped did Jason hit the water? So now I'm looking for this value over here. Okay, so in order to find that, wish I had a little bit more room on here. So in order to find that, I'm going to replace y with 0. Oh dear. And I'm gonna, that's a 480. I'm gonna solve this quadratic. Okay, so, and I'll show you how to do this on the calculator in a minute, but in case you don't have one, or if you're not allowed one, I want you to see that you can do all this by hand. So let me divide both sides by a -16 just to make my life way easier. So now I've got 0 equals positive t squared minus t minus 480 divided by 16 is 30. Okay, I can factor this, right? If I can't factor, I can complete the square or quadratic formula, but this one factors, so that's nice. So it'd be a t minus 6 and a t plus 5. Solve each one. My two values for t are 6 and -5. So remember that t stands for time. And this is what I was talking about, where you're going to get two values, positive 6 and -5. But if you look back here, right, I can't have a -5. That makes no sense. But on my graph, my mathematical parabola does continue back here. So that's why there is a second value. It just, in this real world scenario, doesn't make any sense. So I throw it away. Okay, but it was easy enough to get C, 6 seconds. Okay, that's your basic idea here. I was thinking maybe I'd try the next one. I'll try that one and see if I can pull up that website and show you how to do number 2 on there. You can do it the same way I just did all of this if you wanted, but if you didn't and you wanted to look at it on the computer, okay, let's see, how do we do this? I think if I, website URL, let's try that. Okay, I don't think it's loading. Or is this all that it shows you? I don't know. Maybe I just need to. Let's try sharing my screen and see if that works. Okay, I think this is working. So let's just go to, all right, I don't want classroom, I don't want accounts, just want Desmos is the website that I'm going to. And that's desmos.com. All right, let's go and see. Okay, and I did try this on my phone. I'm using an iPad right now, but I used it on my phone and it works really well. So here it is. You don't have to sign up for anything. You know, I mean, you can download the app, but I don't bother. I don't know if it's free or not. I don't know. Just using the web browser is definitely free though, because I do it all the time. So if you see up in this top right area, it says start graphing. You can just click that and it will bring you here, and you're just going to go ahead and type in your equation. You do want to use X's and Y's though. Don't use the H's and T's because it gets all weird and confusing. So we're just going to type in, they already have Y and X down here for you. If you're using a computer, you just type it like normal. So, oh yeah, if you don't have the worksheet in front of you, you should get it. But here's number 2. Here's what it says. If a toy rocket is launched vertically upward from ground level with an initial velocity of 128 feet per second, then its height h after t seconds is given by the equation h of t equals negative 16t squared plus 128t if air resistance is neglected. And then we're going to answer all these questions about it. So let's go ahead and get the equation graphed. So again, you don't have to graph. You can do it all. And remember, we're going to use x's instead of t's. So there's negative 16x squared plus 128t, but we're using x instead. Okay, so here's the graph. You can, if you're using a phone or an iPad, you can, maybe you can't. Oh yeah, you can. You can just use your fingers to change the window on the graph. So that's kind of cool. Oh, but it looks like it doesn't just let you, if you want to manually change the window, which I do, because it won't let me just change the x-axis without changing the y. So there's a little wrench icon up on the right-hand side, and you can change what you want your x-axis to be right in there. So I want my x-axis, oh, I don't know, I'll go -1. But then it looks like it only goes to, oh, I don't know. We go to 5 on the other side? No, not even. What's the scale here? Oh, 2. I can stop it at 2. So let's change it to 2 here, just so I can see it a little bit better. And you don't have to do this, but I like to. So now I can kind of see what's going on with this. This was a rocket, right? So the rocket's going to start down at 0. It's going to go all the way up to the highest point that it gets, which it looks like it's going to be a little bit above 12. And then it's going to drop back down all under 2 seconds. Okay, so I have this up here. The first question is, how long will it take for the rocket to return to the ground? Oh, that's interesting. Let's actually jump down to C and D, because those are the 2 questions that deal with the vertex. So C asks, how long will it take for the rocket to reach its maximum height? So remember, that is the x coordinate of the vertex. D asks, what is the maximum height attained by the rocket? Well, that is the y coordinate of the vertex. So you could do L by hand, negative b over 2a, plug it back in, get to your vertex that way. Or if you're going to use Desmos, you might as well let it do it for you. And I think, yeah, if you just tap the vertex, a little dot appears, and then it gives you those values. Yeah, it just tells you. I just tapped it. So if you're on a computer, when I tried on my computer, it like automatically, if you just click near there, it gives you that little dot. Okay, so now I have, oh, you know what? I just realized my equation's wrong. Should be 128t. Ah, I had 28. Sorry, I'm gonna have to change my scale. Oh, sorry. All right, so looks like I need all of this for my y's, but my x's, I'm gonna go up to 10. So let me change that. Sorry. And I don't need to go. Let's just go to, let's go like -3 is fine. Okay, sorry. All right, so here's my rocket. Let me double check that I have it right before I keep talking again. Yes, that's right. Okay, now I see it. Now we're good. So again, I'm just gonna tap on that vertex and I think, yeah, there we go. So the highest, it took me 4 seconds to reach the highest point, which is 256. So there's your answers for C and D. 4 seconds to get up there, and it got to 256. Okay, hopefully that makes sense for C and D. Hopefully you had the right equation. Okay, now let's rewind. Go back up to A. It says, how long will it take for the rocket to return to the ground? So this one, I actually already know the answer without doing anything else for a couple of reasons. One, I can see it right on the graph. But 2, since this started at the ground and came back to the ground, well, if it took 4 seconds to come up, it's going to take 4 seconds to come back down. So I already know it's going to be at 8, but if you look at the screen, there's a little dot there. So if you just touch that dot, it'll pop up with the exact value. So this one is 8 seconds it's going to take. And then they have something interesting for B. B is not necessarily at one of my interesting points, the x-intercepts or the vertex. This one asks you, after how many seconds will the rocket be 112 feet above the ground on the way up? So think about it. I'm going to launch this rocket. At some point, it's going to be 112 feet above the ground. It's actually going to happen twice, once on the way up and then once on the way down, right? So they're asking, when does that happen? Okay, so here's how you can find that on Desmos. So if you look back where we typed our equation, if you just click, you can type a second equation. And what I want to know is, when is the height going to be 112? So the easiest way to do it on here is to just type in y equals 112. And that's going to give me, it's going to graph that line for me. Okay, it's going to graph y equals 112. And then I can see a new dot appears where those two meet. So that shows me that at 1 second, my graph is going to, or my rocket is going to be 112 feet up. That's pretty cool. So I can also do that on the other side. I know it didn't ask for it, but if you click the other dot, it'll show you it happens again at 7 seconds, which makes sense, right? It's got a same thing. It's going to go up. It's going to come back down. It's going to hit 112 twice. So you can do that same thing if you wanted to, I don't know, say, gosh, I'm curious, when is this thing going to be 200 feet up? I know it doesn't ask you that, but if you were just curious and wanted to play around, just go ahead and graph y equals 200. Oh, for Pete's sake, the stylus, I swear. I'm just going to use my finger. There we go. And now I could click on those values, so it would take 2.129 seconds for this rocket to get up to 200 feet. And then on the way back down, oh, so cool. So there's so many neat things that you can do with this. Now let's say that you're not using Desmos and you were trying to figure this out without it. Okay, how would you solve the same problem? Well, great question. So let's see how I can get back to the whiteboard now. Stop screen broadcasting. Stop. Yep. Now bring me back to Zoom. Okay, I think I got it. We did a Zoom meeting for Easter so everyone could see my son hunting for dino eggs. And oh my gosh, getting the grandparents, it was torture. So I feel for you as you listen to me struggle through this. But anyway, all right. So my question was, if you're not going to use Desmos, how do you solve the same question? So the question is, after how many seconds, or after how many seconds will rocket be 112 feet up? Okay, so all we have to do, let me just jot down our original function. We are just going to replace h of t, the height of the thing, with 112. And then we can solve from there. So check this out. All right, there's our original function. Let's replace h of t with 112. I want to know, what is the value of t or x when y is 112? So guys, you have a quadratic. You're just going to solve this quadratic, right? So let's minus the 112 on the other side. So now the whole thing equals 0. I'm pretty sure I can divide everything by a -16 here. Let's just check real quick. I sure can. So divide everybody by a -16. And we get positive t squared minus 8 plus 7. Okay, now I just factor this. t minus 7, t minus 1. So that means I have two values for t, positive 7 and positive 1, which makes sense because remember, it's going to hit 112 feet once on the way up at 1 second and then once on the way down at 7 seconds. So they specified in letter B that they wanted it on the way up. So that's how I know that my answer is just the 1 second. Okay, so I hope this helps. And this is pretty much exactly what you're going to do to apply to all of the other questions. Real quick, I'll just help you out with 3. It says you and a friend are hiking in the mountains. You want to climb a ledge that's 20 feet above you. The height of the grappling hook you throw was given by the function blah, blah, blah. What's the maximum height of the grappling hook when you throw it? Can you throw it high enough to reach the ledge? Well, this one, you don't even have to find all these other parts, right? Think about how do you find the maximum height of the grappling hook? Well, doesn't that just happen at, hold on, let's erase all this. So here's the ground. Here's, what are you trying to get up onto? A ledge. Okay, so there's some ledge up here. You're trying to get up there. Here's you. You're swinging around your old grappling hook here, right? That's my grappling hook. Okay, and you're trying to throw it high enough to reach that ledge. So I'm not going to ruin the surprise and see if you can or can't reach it, but it's going to follow the path of a parabola. So you're going to go ahead and you're just going to find the vertex. If at the vertex, this one doesn't ask you anything about time. It just asks, can you throw it high enough? So all you really care about is the y-coordinate of the vertex. Well, you can't get the y-coordinate without the x-coordinate, so you're going to have to find that first. Find that x-coordinate, pop it back in, and see if that is, you know that this is 20 feet up. So can you throw it at least 20 feet? I don't know. You'll have to see. You'll have to do the math. Okay, same thing, same exact thing is happening number 4. It's just a different scenario. This time you're trying to dunk a basketball. So the path that your feet follow as you jump up in the air and try and dunk this basket, follow the shape of a parabola. So we give you the equation of the parabola. You know that you need to be able to jump 2.5 feet in the air in order for you to be able to dunk this ball. So go ahead, find that vertex and see, do you actually get 2.5 feet off the ground? If you can, then you can dunk it. If you can't, then, well, try harder next time, right? So that's the gist. Hopefully you find this helpful. Yeah, and we'll go from there. All right, guys. See you later. Just kidding. I was looking at number 8, and that one's a little bit different. So I know I'm going to have questions on it, so I might as well just go over it right now. So 8's different. It's saying you're going to have a rectangular dog pen that uses 80 feet of fencing altogether. And they want to know what dimensions will result in a pen with an area of 384 square feet. So you have 80 feet to use. Okay, so does it make sense? Like, are you going to do 20, 20, 20, 20? You know, is that going to get you the area that you want? Maybe not. Are you going to do 1 by 80? Is that going to get you what you want? What a terrible pen that would be, right? So you have 80 feet of fencing. You can break it. Oh, wait, that wouldn't make any sense. It wouldn't be 1 by 80. I'm thinking area. Oh, silly goose. It'd be something like if you had 1, that'd be half of 78 is what, 39? 39. Just kidding. Okay. Now we're business. So you have 80 feet of fencing. You can break it up however you like, but you want to end up with a square footage of 384 feet. Okay. And these two obviously don't have that. This one would have 400, right? 20 times 20. This one would only have 39, so that is not ideal. Okay. So there's got to be a way. I'm not just going to guess all the values all day. There's got to be a way to figure this out. Oh, there is. Of course there is. There always is. So I know I have 80 feet to work with altogether. So, and I know it's going to be a rectangle. Do I know how long this side's going to be? No, so I'm going to call it X. Do I know how long this side's gonna be? No, but think about it. If it's a rectangle, that's also x. And I only have 80 feet to work with. So these two sides that I have circled, don't they have to be equal to 80 minus 2x so far? Right? Because it's going to be 80 feet in total, and I can't include those two sides that I've labeled x. So what's left over is 80 minus 2x. Well, the two sides that I have circled are equal to each other, so doesn't that mean that this has to be 40 minus x? And so is this one 40 minus x? Where did I get that from? I just took half of this, right? Does that make sense? And if you add all four of those sides together, don't you get 80? How cool. All right. So to find area of a rectangle, remember that I'm going to just do length times width. So in this case, the area is, what did I say? 384 we wanted? 384. And that's going to equal my length times my width. It doesn't matter who you call length and who you call width. One of them's x, the other one's 40 minus x. Okay, so there is a quadratic that I can solve. Let's go ahead and distribute that x. Let's set the whole thing equal to 0. So I'm going to add these two to the other side. So it'll get me x squared minus 40x plus 384 equals 0. If you were to graph this, it would be a parabola. It would show you all the different areas that you could have with your given parameters. But I just want the one that gives me the square footage of 384. So let's go ahead and, can I factor this thing? Oh, probably. Let's see, and I think 384, let's try. Yep, I got it, 16 and 24. So I'm gonna have an x minus 16 and an x minus 24 equals 0. Okay, so these are two possible values for x. So this side right here could either be 16 or 24. So let's just assume that it was 16. Where does that make this side? If you said 24, you are correct. Well, guess what? If you make this side 24, that just makes this side 16. So it doesn't matter which one you're saying. In the end, it's going to be a 16 by 24 foot pen. These are both in feet. And that's going to get me the desired square footage inside my pen. Okay, so number 9 is similar to this. You have a rectangular frame. Same idea. This one's actually maybe a little bit easier because you don't have to do this whole part. It just kind of gives it to you. All right, so a little bit different. Hope that helps. Let me know if you have questions. Gonna try and do another live Zoom on Friday. So see you there, I hope. Okay, bye.